to talk about education, current education, very essential. Okay, so one of the person, okay, how can I say, what's going on with our education? I only hope that after students get a degree, they can read the newspaper and fill the text form. Okay, and then the reply is very interesting. Reply says, hey guy, according to current trend, soon it will be the requirement for PhD degree. Okay, so there is some tendency so that we tend to do less and get more, but there is no free lunch. If you do less and you still pass the course, it just means you learn less. Okay. Finally, when you get the course pass, you get the degree. That means the degree wouldn't help very much for you to land a job. Finally, okay. So here, I would like to think you more. Okay. So you spend more efforts for the next test, and if you pass that, spend more effort for your university physics too. Okay, I'm not going to teach university physics. I guess Dr. Pizzos will talk with the university physics too, and he will be very strict. In fact, he already retired, but we need him back. Dr. Pizzo, okay, he taught the West Point before. He designed the physics class for the West Point, and he also used the same way he taught West Point students here. Okay, so he'll be very strict. If you don't do your work very well, you wouldn't expect mercy from him. Okay, he's West Point style. Okay. And, okay, I guess the thing is that if you even, I guess, I cannot fill too many students. Okay, I got the pressure. But he doesn't have that kind of pressure. The university wouldn't be able to persuade him to let him go because he's well known for his teaching. Okay, so, and by the way, since there are all the problems, okay, most of the problems you already have, so today I'm not going to go through the problem. If you have a question, you can come to ask me. Let's move to what we are going to learn for the next unit. The last unit okay, is the thermodynamics, mostly thermodynamics. I feel that this is a very useful part. Previously, when we started those things, we started some quite abstract models, like a moving particle. Okay, but in the real life, you don't really deal with some moving particle. You are dealing with more realistic stuff. Okay, and thermodynamics is more realistic. It tries to start with the material of properties. Okay. Like you can think about if you have some kind of gas, what kind of property you will have for the gas, or not in this class, but after thermodynamics, you can move to the material science. Okay, where you can study the material property for like liquid, solid, those things. Okay. I have mentioned before, one of the interesting things to study is superconductor. Okay. How can you make superconductor in room temperature. Once you have that, definitely Nobel Prize belongs to you. Okay, even more. Okay, so that's more important than Nobel Prize. If you can propagate, if you can transport energy without electric energy without any energy loss, that's very good. Okay. So materials is important in our life. So the fundamental to study all the material property is the thermodynamics. Okay. Okay. And here I would like to note a few terminology in the study of the thermodynamics. The most general term is thermophysics. That study everything, include everything to deal with the phenomena associated with temperature and heat. So when we talk about thermal really means temperature. Okay, it's Latin for temperature. So, and of course, with the temperature, you need to talk about the heat energy. Okay, what kind of energy transfer is for heat? When we started the thermal phenomena, that means we started those phenomena related to these two heat issues. Usually, we are going to study the so-called thermodynamics and the statistical mechanics. The first one, thermodynamics, is a macroscopic theory. Okay, so it deals with those macroscopic parameters to describe the material without looking at the microscopic structure. Okay. And the statistical mechanics, I'm going to teach one of the 3000 level physics class. That's the statistical mechanics. It's a microscopic theory of the thermophysics. So the basic idea is that we know everything has some internal structure. It's composed with of atoms and molecules. So the microscopic theory is that if we know this kind of microscopic structure, can we derive those external property for the material? Okay. For example, if I know a particular solid, I know the lattice structure, so many atoms arranged in, let's say, this way, and I know what atoms I have here. Okay. So I know this structure of the solid, and then we should be able to calculate all the mechanic and thermodynamic property for this solid. For example, we should be able to calculate the speed of the sound wave inside. That's a mechanical property. We should be able to calculate the specific heat capacity for the material. That's a thermodynamic property. Or probably we can also calculate the elasticity of the solid, all these properties. And it's possible. We can calculate all these properties for the solid if we know what happens for the atoms and molecules. Okay, how they are arranged. Okay, and what kind of atoms they are. There's a bunch of technique and theory to do these things. So that's microscopic theory. In this class, we only started the thermodynamics. So what happens, what the relationship between those properties, and we're not going to calculate this property from the microscopic theory. Okay. And of course, this is still useful. Okay, even you cannot calculate from the first principle because many of the properties, not many, all the properties are measurable. You can measure them and try to find some empirical relationship, and so you can study more about the material. Okay. First, let's look at, when we talk about material, we have solid, liquid, and gas. That's the most common phases or the states of the matter. Okay. We all know what is solid, liquid, and gas. We have a lot of examples of these things. And here, we would like to put the definition or the characteristic a little bit more clear. In fact, to distinguish solid, liquid, and gas, you can check the volume and shape, how they can be changed by the external force. The solid, in general, you cannot change the volume and the shape for the solid, right? Okay, so the table is a solid, so it has some definite shape, definite volume. And liquid, okay, it has some definite volume. Okay, for most of the liquid, like the water, you cannot compress it, but you can change the liquid shape. Okay, so no definite shape. And gas, no definite shape, no definite volume. You can change the shape of gas. In fact, the shape of the gas is completely determined by the container. Okay, it will fill the whole container. The liquid partially determined by the container. It will not fill the whole container, but just fill the lower part of the container, right? The liquid. And gas, even the volume is determined by the container, right? Because it can fill the whole container. So if you use a small container to hold the sample gas, it has small volume. Or if you increase the container's volume and the whole gas, the gas volume will increase correspondingly. Okay? And if you think about the internal structure, that's related to the strength of the interaction between the molecules or the atoms. For the solid, there are very strong interaction between molecules. Okay? So you cannot compress it, you cannot change the shape. All the molecules will be held into some specific position by those strong interaction. So we can think about like this. If you have many, say, small particles, okay, think about some more. If you hold all these balls with strong spring, very strong spring, this spring represents the interaction between the molecules. Okay, these are molecules or atoms. Okay. So if all these springs are very strong, you can see these forces will hold the space position here. So you cannot easily compress it because you are going to have a very strong force from the spring against your compressing. And you cannot change the shape, okay, because these forces will hold the position of the atoms. So you cannot change the shape. Okay, so that's the representation for the solid, crystallized solid. And if you reduce the interaction, or if you don't have many strong spring here, if you have some weak spring, okay, so you can so what happens is that if these atoms or molecules, they are held by some weak spring, so in general you still cannot compress it, you can change the volume, but you can easily change the shape. So that means each molecule can have some small displacement around the original position. Okay. So that's the representation for the liquid. Moderately strong interaction between the molecules. So they can one randomly, but they will still they will still hold some average distance between them. Okay, so you cannot compress it or break them easily. Okay. For the gas, okay, okay, it has very weak forces between molecules. So what happens is, if it's very weak, for example, you'll even have any forces between the molecules. If you have 9 molecules, you can arrange them like this, okay, with a large container. With a small container, it's okay. They just arrange it like this, very condensed. There's nothing wrong because they don't have forces between them. So you can pack them, right? You can even pack them like this. So no definite volume for the gas. Okay. And by the way, one important thing for the gas is that for the molecules inside of the material, they are not in a stationary state. Okay. They are in random motion constantly. And in fact, these speed are very fast. So inside of your body, there are a lot of those molecules and atoms are actually moving. Okay. But for the solid, because the position is cold, actually for the solid, the molecules are in vibration. Okay. It can be permanently removed from the original position. And for the liquid, they can move to very many faraway places, but kind of combined with other molecules, nearby molecules. For the gas, these molecules or atoms, they move randomly to anywhere they want, total randomly, and moving very fast usually. So that's solid, liquid, and gas. As we mentioned, the most simple one, the most simple state is the gas. Thermodynamics, we will only consider gas. And liquid and solid are more complicated. So usually we start with the gas in the thermodynamics. Then, if you're in some major or physics major, you may take the solid state physics. That will deal with solids. And the most complicated one is the liquid. In fact, superconductivity, superconductor and super fluid, they are some kind of liquid stuff. So, and then it will be even more advanced class to start. And here we will study the gas. But for all these property, for all these things, we need to find the key parameter to characterize them. Remember, when we studied the particle, point particle, there are two important parameters. One is the mass of the particle, Another is the force. Mass is the internal property of the particle. And force is the external agency to change the state of the motion for the particle. Now, we need to extend the notion of the mass and force. Here, when we talk about the material, instead of talking about the total mass of the sample, we would like to talk about the density of the sample. The reason is that if you have the same kind of gas, if you have a large sample or small sample, so they have different mass, different sample, but they may belong to the same material, right? If you have 2 cans of air, this is maybe say 100, 10 kilogram. This is 5 kilogram. So mass will be different. But when we study the material property, we want to study the property specific to this kind of material, air. We don't really worry about if this kind of air or that kind of air. If you double the mass of the air, the gas here, that shouldn't change the essential property of the air, right? So what is the same here is the density could be okay. So the density rho is defined as the mass over volume V. So if this is 2 kilogram and say the volume is 2 meter cube, and this is 5 kilograms, the volume is 1 meter cube. So they have the same density, right? It's a ratio. This is 5, this is 5. So the density is is to describe the property of the material, not each individual sample. Okay? Now, let's look at the force. If we apply some force to an object, okay, if it's not particle, if it's some extended object, so please note that the force can be applied to this large surface, or if we have a small object, the force may be applied to the small surface. The effect actually may be different. Okay. The same force if you apply to a large surface. So each part on the surface will receive less force, right? Okay. If you apply the force to a small surface here, then the effect will be more different. So here, we introduce the pressure. Pressure is the force divided by the surface area. Let's call it A. Okay. But what you need to pay attention to is that to calculate the pressure, you want to use a perpendicular area. For example, okay, if this is the surface, if you apply, let's look at from the side view, okay? Think about this is a cube, and you have some force if it acts like this way. So the force is not perpendicular to the surface. In the case, it's not the whole surface matters to calculate the pressure. The pressure should be the surface perpendicular to the force. Okay, how can we find the perpendicular area? You need to do the decomposition. Okay, so it's this part. Okay, this is the area perpendicular to the force. So if this is A perpendicular, so A perpendicular will be A multiplied by cosine theta. Okay? It's kind of the decomposition. In another way, you can also decompose the force. Okay? So the pressure will be F divided by A perpendicular, or F divided by A cosine theta. Now you can also try to look at the force. It says that okay. Okay. Let's not decompose the force. Let's just stick with this. Decompose the. Okay. So that's the definition of the pressure. But of course, in most cases, we're going to apply the force this way, perpendicular to the surface. In that case, P is simply F divided by A. Okay? Any question here? And now, let's think about the advantage or the why we want to characterize this force per unit area. This is actually a force per unit area. This is a mass per unit volume. Okay. Because of this effect. For example, the salt. Okay. Salt looks like this. Okay. Why you want to have some tip here? Why you don't just make your salt like this? Okay. Because, okay, when you use this salt and this salt, you can apply the same force, right? Say if you can apply 100 Newton here, 100 Newton here. Okay. But what happens is that then when the salt to cut something, the pressure will be different. If you use this to cut it, say like say at the top the volume is 100 whatever. Okay. So then the pressure will be 100 over 100 equals to 1. Okay. And here you have very small surface T. Okay. So the pressure will be reduced. 100 divided by 1 equals to 100. So you will produce a large pressure, so it can cut through the body. Okay. So here the effect is determined by the pressure, not the total force. Okay. To prevent, and also on the other hand, why do you want the armor? Okay. In fact, how the armor works is like this. The armor cannot reduce the force. Okay. If I use 100 force through the sword, this one or this one. Okay. Anyway. It cannot be reduced. All the 100 force will be propagated to my body. But if you wear an armor, what happens is that this 100 force will give to the armor. This armor is some rigid object. Okay, if it's not broken, so the 100 force will be spread out through the whole armor. Okay. So now, instead of just receive the force at this large surface area or this large area. Now I'm going to receive 100 force throughout my whole body. So each part of my body receives almost nothing. Okay. So it's all about to change the area so you can change the pressure. So that's the pressure. Okay. Now, after we introduce the two important parameters, the density and the pressure, that will be very useful to characterize the material. Okay. Now, the key definition, the key term we need to know about the thermodynamics and temperature. Okay. Temperature, we all have the idea what it refers to. It refers to hot or cold. Okay, high temperature means hotter, and low temperature means colder. Okay, so it's some quantitative description of hotness. So if you give some number, so you can say hot or cold by like 100 degrees hot, 0 degrees is cold. Okay, some quantitative description. And but the interesting thing is what we mean by hot or cold. What exactly is? It's related to the molecular motion. Okay. The hot, in fact, means the molecules. If your body is hot, actually means the molecules is moving faster inside of your body, the random motion. Okay, to all the direction. And your body, if your body is cold, means the molecules inside our body is less energetic. they are moving slower. Okay. So the microscopic definition of the temperature is a measure of the average kinetic energy of the atoms or the molecules inside of the object. Okay, the average kinetic energy. Okay, so it means kinetic energy is 1/2 mv squared. So it means larger kinetic means energy means moving fast. And in fact, this is related to like fever. Okay. When you catch cold, you will get fever, right? Your body temperature will increase. In fact, fever itself is not completely a bad thing. It's, I think you know, it's the body's natural reaction through the immune system. It's to try to kill the bacteria by some of your some molecules inside of your body. Okay, I don't know what kind of molecules they're using in your body to kill the bacteria. Okay, but you can see the key idea is that for those kind of molecules, there's some special name for those things. Do you know what's that? Those molecules in your immune system.
White blood cells. I believe they're white blood cells.
Okay, yes. White blood cells do this work, but there is a generic name. Okay, but whatever. Like for
Phagocytes. Phagocytes.
Okay. I don't know what. White blood cell, at least I heard. But whatever. Okay, the molecules. You think about it. For those kind of molecules to work, they should be able to move fast, so more energetic, so they can catch them out, or they can have more chemical reaction to release more energy. So that's why your body temperature has to increase, okay, to excite those molecules, so you can work better, okay. So you can see here the temperature is related to the motion of the molecule. Okay. Well, of course, the bad thing about the fever is that if the temperature keep increasing, now not only the bacteria will be killed, even your body's own cell, okay, will be killed. So you cannot raise your temperature too high. Okay. Now, some important thing related to the temperature is so-called the thermal equilibrium. Okay, what do we mean by the thermal equilibrium? If you have, say, some cold water here, 0 degree, okay, and you have some hot water here, 100 degree, okay, if you mix them together, finally, they will reach some temperature between, okay, let's say 50 degree. Okay, this means thermal equilibrium. So if you bring two objects with different temperature into contact, thermal contact, finally, the temperature, both of the temperature will change. Okay, 1 increase, 1 decrease to reach some temperature between them. But which is the terminal temperature determined by also by the mass, the size of the two objects. Okay. Here, if they are the same, it will be exactly between them. But if you have a small cup cold temperature, a large cup hot temperature, so for this one, the final temperature will be larger than the 50, right? More close to 100. It's also determined by the size. But here, the thing you have to know is that finally, when they reach the equilibrium, they should have the same temperature. Okay. It happens also for any kind of object. If you have like two, like say, iron block, One with 0 degree, another with 100 degree. So after a long time, so this will be like 50 degree. This will also be 50